It is my pleasure to introduce the second speaker of the seminar, Adam Bobrowski. And I think she will talk about something which went on archive this morning, right? At least I think I saw it this morning. Two very recent approximations of Walsh's spider process.
Yes, thank you, Cordina, and thank all the organizers for inviting me here. This was a really nice time in Cambridge and a very fruitful one. So I really enjoyed it. Thank you so much. I would like to dedicate my talk to the late Jan Maria Kiseński, who died 2 years ago, and he was my teacher and mathematical friend. Okay, so I would like to speak about two fairly recent approximations of Walsh's spider. And I need to admit from the very beginning that I was uneducated, meaning that I didn't know that what I have constructed is a Walsh's spider process. I just discovered two approximations of this process, and I simply didn't know the literature well. So it was only recently that I have realized what is there. Approximations were coming from completely different intuitions than Walsh's spider, the original definition. Okay, so let me just first of all, so my talk is in 3 parts. First of all, I will recall what is Walsh's spider process, and then I will tell you about two approximations. One approximation will be by so-called snapping out Brownian motion. In the literature, it's also called Brownian motion with hard membrane or Brownian motion with semi-permeable membrane. So that's one approximation, just 3 different names. And the other approximation is by a kind of kinetic model of a phonon. Okay. So what is skew Brownian motion? Probably everybody knows here, but just to recall, the Brownian motion, the skew Brownian motion is constructed from the original unrestricted normal Brownian motion by flipping excursions from 0. So we have a parameter alpha between 0 and 1, a probability, and for each excursion from 0, we decide whether it's going to have a sign plus or sign minus. So just some parts of the graph are flipped up, and some of them are flipped down, okay, with probability alpha. And it turns out that this is still a Feller process, and its generator can be described by this boundary condition. This simply means that we still have a one-dimensional Laplace operator, but boundary, its domain is composed of functions that are twice continuously differentiable on both half-lines, but at 0 have different derivatives with such a relation. Oh yeah, there is a prime missing, yes. Sorry, thank you. Okay, so this construction was given by Ito and McKean, and there is also a couple of years later, Portenko has discovered the same process as a kind of generalized diffusion. And Walsh has, I will speak about Walsh more in a moment. His paper made this process really famous, and many people started to look at this process in more detail. In Ito McKean, this is just an exercise. Okay, so there is this. I think Andrew have shown this approximation during his talk. Also, there is this very nice approximation of skew Brownian motion by Harrison and Sheep. Everybody knows that if we have a random walk, symmetric random walk, from each point we go to the right or to the left with probability half. And if we have diffusion scaling of this process, then we obtain a Brownian motion. Now, if we change this procedure just at one point, simply by requesting that at 0 we go to the right with probability alpha and to the left with probability 1 minus alpha, and everything else is the same, in the limit we obtain skew Brownian motion. Another, I have just learned about this, Andri's approximation. This is very neat also. So we start with regular Brownian motion, and independent random IID random variables with expected value finite. And the construction is as follows. For each epsilon, we consider the following, each epsilon larger than 0, we consider the following process. Initially, this is like a Brownian motion, but we wait until the Brownian motion hits 0 for the first time. Once it does, we restart the process at a random point. This random point is epsilon times x1, where x1 is the first random variable. Then we run the process for some time again until it reaches 0. And again, we restart and let it run again. So it turns out that if you let epsilon to 0, this these approximating processes converge to skew Brownian motion with this parameter. Okay, so coming back to Walsh, once we have these intuitions, we can think of a more general process. We think of a spider on a web that goes to the web center as performing a Brownian motion, but once it reaches the origin, it chooses one of the rays with probability alpha I. These probabilities add up to 1. So, so this is, of course, a generalization of what was shown before, just to, instead of 2 rays, we have as many as we want. Actually, Walsh's process is on the entire plane. So you can go in any direction, and instead of sum of probabilities, you have a distribution of those probabilities. Okay, so this is something I didn't know up to, I don't know, 2 years ago, and so I had to start with something completely different. So this is like in around 2010, I have heard about a model of so-called neurotransmitters, and in this model, actually there were 2 models. One of them was this one on the right-hand side. This was like a compartment model, and there were 3 different ODEs describing how many quad-quad vesicles or neurotransmitters are in 3 different poles. Okay, and there was a system of differential equation describing how they change in time. And there was a new model that was in PDE form. So you had a kind of diffusion in some region, and the authors were claiming that if you integrate over a certain region here, certain region there, and certain region over there, you will obtain this the system that was already known. Okay, so you go from a PDE model to an ODE model by integrating. But I didn't believe it. And actually, when I looked at the proof, the proof contained a large gap. So I was trying to find out how is it possible to go from a PDE to an ODE model. So first of all, I realized that I need to have some kind of boundaries here. There must be something, some kind of I was thinking about semi-permeable membranes. Okay, there must be something, and I need to describe how the process behaves at the boundary. Yes. So what happens when it goes from one region to the other. Okay, it was clear from the description that at 0 I have to have a reflecting boundary. At R1 I had to have a kind of this is elastic boundary, so that some process leaks out. But these in red was something that analytically was the only thing possible for the approximation to work. My idea for approximation was not integrating over, but letting diffusion coefficient to be very large, and at the same time transmission through boundaries quite small, so that in the limit, oh, I didn't say that. Okay, if you look at this system, this was a system of ODEs. But if you look closely, there is an intensity matrix of a Markov chain hidden there. And here you have a diffusion. So of course, I was thinking I need to have, from diffusion, I need to go to a Markov chain. So I kind of, each region has to be kind of combined into one point, and in the limit, I will have a Markov chain. So it actually did work. You need to tune the parameters, but it works just fine. But this is just a side story. The main fact is that I have, quote, quote, discovered these boundary conditions. And I need to, and these are precisely the boundary conditions for, that I will describe in a moment. These are boundary conditions for what Andrew calls hard membrane, and in the literature it's also known as snapping out Brownian motion. But let me just comment that, okay. Okay, so I wanted to understand these boundary conditions, and I looked at them from the point of view of Feller boundary conditions. This is classical theory. So it turns out that, if you want to understand this process, we need to split this process into simpler ones. And the simplest one would be this. I have just one membrane, and I have a diffusion on the left-hand side, and I have a diffusion on the right-hand side, and some kind of transmission from going from the right to the left and from the left to the right. So I have two coefficients that will describe how permeable the membrane is. So I think again of a membrane at this point, and I kind of want to describe how particles filter from the right to the left, and vice versa. So it turns out that this, if you look at the Feller boundary conditions and their description in probabilistic terms, it turns out that this process is like this. We start a Brownian motion, say, on the right-hand side, and we wait till it touches 0 for the first time. From that time on, we calculate the time it spends at the boundary, meaning at 0. So this is a local time, Brownian local time. And once this time exceeds an exponential random variable given independent, it filters to the other side. And again here, we calculate this time spent at the boundary, local time, and then when this time is sufficiently large, we jump to the other side and start a Brownian motion there. As you can see, these A and B, these parameters are here. So they are really permeability coefficients. They tell us how much time do you need spent at the boundary before you filter to the other side. Okay. So the larger is A, the larger, this is going to be important in a moment. The larger is A, the shorter is the time you need to spend at the boundary before filtering to the other side. Okay. And I need to add immediately that these transmission conditions are very well known in the literature. I mean, this is not a new discovery. This is already published. I mean, in the old book by Crank in 1975, these conditions are already there, and they simply express Newton's law of cooling. And there are countless papers on this. Diffusion through membranes, absorption and desorption phenomena, you just name it. Just so many. There is also there is a number of papers by Breslov who describes certain process in biology with this type of boundary conditions. What was missing, and this is probably the only thing that is new in my paper, is that I gave a probabilistic interpretation of this. So I was able to describe the process behind this. So 4 years later, there are two papers that appear in the literature. Andrew Lijai, he constructs this process. I just described the process. I didn't construct it. I thought this is obvious that it's going to be like that from the Feller boundary condition theory. So Lijai has described this, has constructed the process and called it snapping out Brownian motion. And there is also a paper by Andri, and he constructs an approximation of this process and calls it Brownian motion with hard membrane. So let me now, so a couple of years later, in 2015, before the papers that I have just mentioned were published, I was thinking about, so actually, this is, okay, there was a special volume to be published by dedicated to a friend of mine and a great mathematician. So I had to come up with a paper. So I was, I was thinking, what can I write? So I was thinking, okay, what will happen if I take this A and B very large? Since these are permeability coefficients, if I take n large, multiply by n, and let n go to infinity, I should probably get a Brownian motion. Yes, just a regular Brownian motion, because permeability is infinite. So, I mean, it's just going to pass through the membrane without noticing it. Yes, this was my thinking. But even if you look at these conditions, it's obvious. It immediately becomes obvious. Of course, it became obvious to me after several calculations, and I didn't get Brownian motion in the limit, so I was trying to understand why. So if you look at these boundary conditions, you immediately realize that two conditions have to be in the limit. First of all, f of 0 plus must be f of 0 minus, which is not surprising. But the other one is just by looking at these two. So we have some kind of asymmetry in the way, even though permeability is infinite, in the limit you have some kind of asymmetry between the way particles filter to the right or to the left. So I was actually referring to Orwell's, there are all animals are equal, but some are more equal than others. Okay, now if you look at it, now we know this is just skew. This is simply skew Brownian motion. Yes, so we have this first, but this is not recent, almost 10 years ago. So there is still something to cover. What is new? What is new? Just a recent result from this year, actually 2 years ago or something, but published just to be published soon. Okay, it turns out that these snapping out Brownian motions are of very special form. I know you are more probabilists than in functional analysis, but for semi-groupies, this is, I am a semi-groupie, for semi-groupies, this is something quite natural. Some semi-groups can be obtained from so-called cosine families. Okay, like if you have this is Weierstrass formula. This is like if you have a wave to the right and to the left with probability half, then it's just a Brownian motion if you just kind of randomize it. So it turns out that these snapping out Brownian motions are also of this form. I need to add immediately that not all semigroups are of this form. Very special semigroups are of this form. Only some of them, very particular ones, are of this form. And it turns out that, first of all, these snapping out Brownian motions are of this form. And secondly, not only the semigroups converge, but also these cosine families that are hidden inside. Of course, if you have any property of this cosine family, then it immediately transfers to the properties of the semigroup, but not vice versa. So this is much, much stronger than convergence of semigroups themselves. But I do not have a clear probabilistic interpretation, sorry. But it speaks of kind of regularity of this convergence. This is much, much deeper convergence than just convergence of distributions. There's something more going on here. Okay, and very quickly, another result from this year. We can generalize this result from the previous slide to the Walsh's spider process. We can actually generalize it to the case where this spider process is somewhat, I mean, the center is somewhat sticky, so that the process, when it hits zero, it has a tendency to linger there, and then to decide where to go farther. We can approximate this by snapping out Brownian motions as follows. We have a number of half lines, and on each line we have a sticky Brownian motion. And once zero, I mean, the local time at zero is again calculated, and once it reaches certain level, then the process jumps to one of the remaining lines with equal probability, okay? And again, so this is the boundary condition that describes this process. And again, if you multiply this permeability coefficient by n, in the limit, what happens is that all those points at the ends of the intervals, they kind of get glued together. They become one point because jumps are immediate, quote, quote, in the limit. So all these points are identified, and we obtain a cobweb. And these are the parameters that are in the limit. And again, the same can be done with convergence of cosines that are hidden there. But to do that, you need to have these AIs equal 0. It's just, the problem is that, okay, perhaps I should have told you, these are all contractions, because these are Feller semigroups. But these cosines do not need to be. So the biggest problem is how to find a common bound for these. And so we need to go very deeply into functional analysis, blah, 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 to do that. Okay. So I think I'm fine. Okay. Oh, so this is the first part. For Walsh, yes. I mean, not only for Walsh, but also for. This is some kind of. This is very similar to a wave. Okay. But you need to look at it from a very particular perspective.
How is when you do approximation on the previous slide? So where NP is there when you do weight?
Yes, these are permeability coefficients, and if you multiply them by n or 1 over epsilon and let to the limit, and so this simply means that times that are needed for the process to go from the end of this half line to the other are very shorter and shorter. Yes. Okay. So this is the third part of my talk, or the second approximation. It's a very nice story. It started even back in 1950s. There was this mathematician called Samuel Goldstein, and he noticed that the telegraph equation has properties. This is a hyperbolic equation, yes, but its solutions have properties of parabolic equations. In particular, if you start from a positive initial value, all the consecutive values are going to be positive. So it's like in a Feller process, yes, or a Markov process if you look at the expectations. So this was a kind of mystery for some time, and then Mark Katz came into the field, and he actually gave a direct explicit formula for the solutions. Okay, this is in terms of what is now called Poisson-Katz process. Sometimes we have a Poisson process with expectation AT, and this is a process of it's either under the integral you have either -1 or +1, and okay, if A is what? If A is 0, this is psi A of t is t. So you have a solution to the wave equation here. Yes? So the wave equation is for A equals 0. This is just a wave equation. Yes? And then, so we have, this is a kind of forcing term. And, oh, sorry. So this forcing is hidden in this stochastic kind of, you can think of particles that are bouncing from something, yes, at random times. This has been a huge thing. I mean, this book by Mark Katz, where this was published, started a very important field for a long time. A number of mathematicians was working on this, particularly Grigor and Hersch. They have started the theory of so-called random evolutions. Okay, so this was a big field. But I would like to tell you about the approach to this problem by Jan Kiseński. This is very neat. Namely, he added a new, the second coordinate to the process. This is this Mark Katz's process. And if you add this new coordinate, then this is a process that has values in r times -1, 1. It turns out that you can introduce multiplication in this set to make it a group, a non-commutative group, and this process becomes a Levy process then. This is just amazing. Yes, this is a Levy process, but you need to take increments in the sense of a group, not just, if you look at it without this coordinate, this is a Markov process, but not a Levy process, of course. Okay? So let's look at this group. This group looks like this. You have an upper line and you have a lower line. And this process is moving along. These are typical lines for this, yes? I mean, this is a typical motion for this group. You go to the right on the upper part and you go to the left on the lower part. And at the epochs of Poisson process, you jump from one line to the other. Okay? So this is this Levy process. Okay. So this is what is hidden behind this Samuel Goldstein discovery. Okay. So now let us think about something more about it. Okay, if we look at this, again at this telegraph equation, and we take v squared equal to a, so this is going to become a, and we let a to infinity, heuristically, in the limit, we will obtain diffusion equation. Okay, and you can make it precise. You can prove a formal theorem saying that this process of going on this Levy process, if you scale it appropriately, in the limit you will obtain a Brownian motion. There is one interesting feature of this approximation, namely the approximating processes have values on two lines, but in the limit the process is just on one line. Why? Because jumps are so frequent between these two lines that in the limit they are kind of merged. Okay, it's kind of state space collapse. Okay. So I'm able now to speak about recent development. So this is a model that we were studying with Tomasz Komorowski, my older and very well-known friend. So the inspiration came from models of kinetic motions of phonons through interfaces. Okay, so this is actually just a simple modification of the process that we were already that was already described. Again, a process moves to the right on the upper part, moves to the left on the lower part, and there are jumps from one side, from the upper to the lower, and vice versa. But we have an additional stochastic what should I say? So another stochastic mechanism, namely, if a particle approaching, we think of this as an interface. So if you approach this interface from the left, then with probability p, you still are going to the right, or with probability 1 minus p, you jump to the other side, to the lower line, and go to the left. And the same on the lower line, you go to the left. With probability q, you pass through the interface, or with probability 1 minus q, you go to the upper part and go to the right. So, of course, there must be some, from the previous investigations, it's somewhat clear that we should have a Brownian motion in the limit, but behavior at the interface is a kind of, well, isn't absolutely clear from the very beginning. Oops. Okay, almost. You will not be surprised to learn that in the limit we obtain skew Brownian motion. Otherwise, this wouldn't be presented in this talk. So this alpha is p divided by p plus q. Okay, and so this was 2 years ago, and now the following generalization was proved by me and my colleague Ela Ratajczyk. Namely, we're trying to think, how can we generalize this model, this approximation, to the case of Walsh's spider? Okay. There I had just, from 2 lines, we went to 1 line. And here I have several arrays going from 0. So how do I approximate this? Okay, it turns out that you can do this. This is for k equal 3, but the picture is just for k equal 3. I mean, the number of edges equal to 3, but this of course works for any k. So what we have is we have say if I want to have a Walsh's spider on the graph with k edges, I start with k copies of a web. Okay, k copies of this star-like graph, and on the first, and I distinguish one particular edge on which the process always goes towards the center, and on the remaining ones it always goes outside of the center. I mean, from the center. Okay. On the second copy, this line is distinguished, so that on this edge I go to the center, and on the other ones I go away from the center. And the same here, I go towards the center and from the center on the remaining ones. So once I suppose I'm on the upper copy, if I approach 0 from on this edge, then I have a matrix P of probabilities of going to different edges. And I have also this P includes a term that tells me that sometimes I will not continue my motion on this copy. I will go to the other copy. This is term P11. Okay, and the same here. I will have P22 is going to tell me that I'm not going to continue on this copy, but jump to some other copies. Okay, and also I have R. R is is the probability matrix that tells me probably, okay. So R tells me where I go. I mean, P tells me whether I should be on the same copy or should jump to the other copy. R tells me precisely where I am going if I jump to the other copy. And I also have Qs on each copy. I have intensity matrix telling me when I should jump from corresponding points. Say I am here, and I can jump from here to either here or there. Okay, the same distance, just different copy.
Intensity. So is it diagonal or all?
This is almost. I will show it in a moment. That's the only thing I need to know is that if I so from the jth copy, if I jump to every other copy with the same probability. Okay, so this is what it says roughly, but the rest is just any matrix, just symmetric. That's.
You think where to jump.
Yes.
And sometimes you go to the right.
No, not where to jump, but when to jump.
When? Yes, when. Only on.
Yes.
And the speed of going left or right, is it 1 or?
Yes, well, actually, if I remember correctly, on this it has to be k times larger than on the other ones. Something like that, yes. So the speed on this one is larger than the speed on these. They kind of slow down. After going through 0, they kind of slow down.
But when you return?
When I return, it's again a large speed. Okay, and this P and Q must be related by some kind of condition. It's just something that came up technically, but it's very similar to detailed balance condition. So in particular, it implies that those alpha i's are going to be, the vector is going to be invariant for P. Okay, and the result is as expected. If you do diffusion scaling of this process, in the limit you will obtain Walsh's spider process with alpha i's as probabilities for this limit process. That's it. Thank you very much.
Yes, can you go back to your probably very first slide?
Very first?
The very first example that you gave with that converges to the Brownian motion.
You mean Andres or
Even I think even before.
that one?
Yes. So in what sense is the convergence? Is it weak convergence or?
Yeah, that's weak convergence, yes. Yeah, this is Harrison and Ship 1981. I can give you the paper, of course.
Two questions. One is, can you, in the next model, in your cell you get Walsh.
Which model?
For Walsh, yes. You consider 1 over k minus 1. Why can't you consider non-uniform?
1 over k, yes,
Non-uniform. In the limit you have stationary distributions.
Yeah, we just took the easiest way out. That's.
I saw paper by Bobrowski with authors who consider telegraph equation, but maybe with Levy flights, I don't remember.
I do not know the paper, but
It's very fresh.
Okay.
2024.
We
But-
can,
But,
yeah.
but I don't, just took a glance a week ago.
We'll talk about it later. then.
So why was it, I missed the point, of why was it important that you would, the telegraph process, why, you would put it in a group somehow? Why is this important? How do you-
Well, it's just the way to explain this phenomenon of telegraph equation. If you have, of course, you can do without it. You can just say that this process coined by Mark Katz, that this is all you need. But I think it just gives you a better insight. Yeah. So okay. So this is a Markov process, and you can just stay with that. That's it. Yes. But then this beautiful picture is not in place. I mean, I think this is just beautiful to have a Levy process with values in a non-commutative group.
The next result, can you associate with certain Levy process?
Nope, nope. I hoped so for a moment, but of course this changes everything. Plus even if you look at the Walsh's spider, I mean, this would need to be I mean, this picture would need to form a group. So, and there is no way, I mean, on a Levy group, on a Lie group, you have natural motions along curves of Lie group, yes? But here you don't, because there is this point where they kind of split.
Yes,
So,
it's full of everything, but before you hit, maybe you have something with the
okay, yeah, but again, you would need to know, if you are on a group, you know where to go. Yes, that's the integral curves. For each point, you have only one integral curve. Here, apparently, you have several, so it cannot be a group. It cannot be a Levy group. I mean, Lie group.
R2 times z over nz,
Mm-hmm.
and like the point n will basically go in the direction like
Uh-huh.
potential I and like k over n, something like that. So like you will go like in this direction, and then you suddenly will jump and go in the next direction, and then the next one.
But is this a group? I need to think about it.
Yeah.
Let's take the speaker again.